Aloha and welcome to our video on stellar evolution. In this video, we'll identify which stage marks the birth of a star, we'll explain why all stars eventually die, and we'll list the possible stages of a star's life cycle. Okay, so here what we have is a picture showing the life cycles of a star, and what we're going to do is we're going to start off with our dust and gases forming our nebula here. So this is going to be our first stage. Now, gravity is going to pull this dust and gases together, and it's going to continue to do so, and it'll get larger and larger, and you'll have more and more mass coming together. And ultimately, what's going to happen is you're going to have a protostar occur. And a protostar is where you start seeing nuclear reactions will start to fire. It gets hotter. You can see this separation from the rest of this dust and gas cloud. So there's an actual difference there. Once that happens, it's going to continue down the protostar. You're going to see this isolation. It's going to continue to squish a little bit more. And then we reach this equilibrium of forces. And that's when we have the birth of our main sequence stars here. Now our main sequence star is going to take the rest of this hydrogen and it's going to convert it to helium. And then when that runs out, what's going to happen is you're going to have less explosion on that star. So it's going to want to compress down a little bit more. And as it does so, it'll do so until it starts to convert helium. And once it converts that helium or burns that helium and makes the larger elements, once that occurs, we explode upwards in size and get into our giant stage here. Now our giant stage is going to use up this helium that it's burning, and then when that helium burns up, then we get this compression again. And then depending on the mass of the star is where it's going to end up. So here we're going to go through a variable stage. Eventually we'll flare out and form a planetary nebula stage. We may go to a white dwarf, and ultimately the white dwarf will cool off to a black dwarf star there. So we talked about these nebulas as being the birthplace of stars, and here we have these nebula, and you can see the gases and the dust clouds that are there. And what's going to happen is that's going to compress down and it'll form a protostar stage. And then once that protostar stage compresses a little bit more, we get to these equal balanced forces. That's when we have our birth of a star. So here we can see probably a star here. We'll see a couple stars over in here as well. But you'll see that this is where our birthplace of stars occurs. Now, when we're talking balanced forces, what we're looking at is we're looking at a balance of gravity, which we'll see in blue here, compressing and pulling all of this stuff towards the center. So gravity is going to be working this way, and then we'll have this gaseous radiative pressure here from this explosion inside that's going to be forcing it out. So when they equal, then we end up with a main sequence star that's going to be about the same size for a while as it's burning. And that's where our sun is. Our sun's not going to change size an awful lot right now. When it runs out of hydrogen, it'll compress down, and then when it converts to helium, because it's a bigger reaction, it'll actually expand the size of the sun that way. So once again, looking at our life cycle, we see that we have this gas and dust cloud, and we're going to have gravity pulling it in this way. And that gravity is going to do so until we get to about this stage here where we have the protostar. And in the protostar, we see a little bit of light coming from there, but we're going to experience some expansion and contraction of that star. So in this protostar stage, we're going to have a small star, then it'll explode out to a larger star, then back to a small star, back to a larger star, and it'll kind of level itself out until these forces balance. When that happens, we get a main sequence star right here. Okay, so that's like the birth of a star right in that area. And then we'll kind of travel through our giant phase, and like we said, we'll peter out. And it kind of varies on the mass of a star. That's the big determining factor. Okay, so let's begin and look at a low mass star. Now, a low mass star is going to start off as a nebula, which we see here, and it's going to compress down through the protostar stage and form this main sequence star. Now, because it's low mass, that means that it's going to use its fuel at a low rate. And because it's using it at a low rate, they're going to have these long lifespans. And in fact, we have some of these stars that are burning, and we think they may have started right after the Big Bang. So they've been burning for about 12 billion years, and they're still burning through. Now, what we notice is over time, they're going to use this hydrogen up. And as they use this hydrogen up, these balanced forces aren't going to remain that way. So it'll compress down to a white dwarf where we'll still see some light being produced, and we can see some of these out in the universe. And then we think that it'll cool further and form what we call a black dwarf. And a black dwarf is just going to be a burnt out star, But we don't see any of these because we don't think that the universe is old enough for any of these to occur yet because of this low rate of burning that we see in these low mass stars. Now, if we look at a medium mass star, and that's going to be kind of like our sun here, what we'll notice is it starts off as a nebula here, and then we're going to compress down through the protostar, form our main sequence stage, and it's going to burn a little bit faster because there's more mass, and it'll actually come down, and when it runs out of hydrogen, it'll compress down and we form this red giant stage. Now, a medium mass star is going to burn through the helium, and it burns through the helium a little faster than the hydrogen. And what will happen is with a medium mass star, we end up with a planetary nebula. So when the red giant goes, it'll compress down and then it'll kind of like fizzle out to a planetary nebula. And from there, in the middle, we'll have our white dwarf formation, and then ultimately we can go to a black dwarf this way as well. Okay, so now let's take a look at massive stars. Massive stars have so much mass that they're going to burn through their material quicker, so they have a much shorter lifespan. So when we compare like a low mass star's lifespan where it may be longer than the universe has been around, a massive star is going to have a much shorter lifespan comparatively speaking. Now, these guys also start off as a nebula. You're going to have this contraction through the protostar till we get to the main sequence stage, and then it's going to burn through the hydrogen a little bit faster because of its massive size. When this happens, it'll explode, but instead of forming a red giant, it'll form what we call a red supergiant. And a red supergiant example would be like Betelgeuse in the constellation Orion. Now, this will burn through the helium, and it'll make the heavier elements, and then once it runs out, it'll compress down again, and then we'll have this violent supernova explosion. So we'll look out into the sky and we'll see this star just go super bright. Some of these are bright enough that they've been reported seen during the daytime. So we haven't had one that bright in hundreds of years, but Betelgeuse could go at any moment. So we might have the opportunity in our lifetime to see these. Okay? Then this supernova, depending on the size of the star, will compress down into what we call a neutron star, or it might even continue to compress down a little bit further all the way to a black hole. So now when we look at our picture of the life cycle of a star, what we're looking at is that of a medium mass star. And you can tell that by noticing the planetary nebula stage here, the white dwarf, and ultimately the black dwarf stage. And if you look at this, this kind of looks a lot like our HR diagram, where we have our main sequence coming through here. We're going to have magnitude or luminosity on the sides here, and our surface temperature here, where we have our 3000s to our 30,000. So you can see how the HR diagram we showed you, there was this main sequence here, we had our giants up in here, and then we had our little dwarf stars down here. So you can see how it shows that the HR diagram kind of depicts this evolution of the stars. So in this chart that you'll see in the lesson, this is the key here, this initial mass of it. What's going to happen is if the sun is 1, so a star like our sun, its main sequence is yellow, which is what we see, it will have a red giant phase. After the giant phase, it'll go into a planetary nebula stage, and then ultimately we'll end up with a white dwarf. If we get a larger star, like 6 times the mass of our sun, then we have a white burning star. It also has the giant phase. It's going to go supernova, but then it'll compress down to a neutron star. And a neutron star is the densest thing that we can see or we can record in the universe. If we go more massive, like 20 times our sun, then we have a blue star, so something like Deneb that we saw earlier. It'll have a supergiant phase here. It goes supernova, and then ultimately it can become a black hole here. So our black holes are going to be the results of these supermassive stars, these 20 times the size of our sun. So what is a black hole? Well, a black hole is going to be an object in space, and we call it a singularity, which means that we're taking an entire star and we're compressing it down into the size of a dot, of an infinitesimally small little dot. And that's what we call a singularity. It's going to have such high density that it's going to create a gravity around it that you're going to have what we call an event horizon. So our singularity is here, and then we're going to have this boundary around it that we call the event horizon. And anything inside of the event horizon will be pulled into this singularity. So light itself cannot escape from this one. And a lot of times around this event horizon, we have what we call an accretion disk, and you'll see this orbiting disk here in the picture. And that's what they're talking about, this one right here. This black hole is actually, the accretion disk is pulling off from a red giant. So it was probably a binary star system. One of them collapsed down to a black hole, and you can see that mass is being pulled from this red giant down into this accretion disk here, where it will ultimately fall into that singularity, and that'll only cause the black hole to get a little bit larger. Now, black holes are also interesting because we've hypothesized that at the center of the galaxy is a supermassive black hole, and that's what causes the galaxy to be rotating as we see it. And we'll talk about that a little bit more in the next video. For now, enjoy the lesson and good luck on your quiz, and we'll see you in the next video.